Okay, so here's what is different with the sheet that I just gave you. Okay, this is also a standard reduction chart, but what's different from the blue sheet, your blue sheet basically only has the elemental forms and stuff. The only exception is that you have water that's listed on here. Everything else is pretty much just the elemental forms. This one that I just gave you is more useful because of the fact that this has, for example, if you look at the like MnO4, so this has MnO4 turning into MnO2. It has lead oxide. It has MnO4 turning all the way into Mn2 plus. Okay, so this one not only has the elemental forms on it, it also has often the complex anions or complex cations that are capable of acting as reducing agents or oxidizing agents. Now, but it's the same thing. So let's look at a trend. So you have fluorine turning into fluoride 2.87. That's at the top. And then you've got, let's say, for example, a little bit farther down, you've got bromine, and that can gain 2 electrons and turn into 2Br minus, and that is 1.09. And then you've got, I don't know, K plus an electron. K plus sounds like a K-pop band. Negative 2.92. Okay, so if I ask you to look at a chart and say, where are you going to find the best reducing agent? And you have 4 options, okay? I want the best reducing agent. Would I look at the top left, like on the reactant side? Would I look at the top right, product side? Would I look bottom left, product side? Bottom right, bottom left reactant side, bottom right product side. Best reducing agent.
Somewhere in the bottom. Right.
Somewhere in the bottom. Well, let's just discern this. If I ask you to find the best reducing agent, what do I want that substance to do? Gain electrons or lose electrons? Because reducing agents are easily what? Oxidized. You got to flip that. Okay? So reducing agents are easily oxidized. Oxidations involves the loss or gain of electron. Loss. Okay. Now, let's look at this. Do you think fluoride ions would be good reducing agents?
No.
Why?
Because they want to gain.
No. Fluoride ions. Would fluoride ions be good reducing agents?
No.
Horrible. Why?
It has a big voltage.
Yeah. How does it want to exist? It wants to exist as fluoride ions. It wants to exist as fluoride ion. Okay? It does not want to lose an electron and go back into the elemental form of fluorine. So fluoride ions would make horrible reducing agents. Okay? Now, think through before you answer this one. So we've established that fluoride ions would make horrible reducing agents. Would they make decent oxidizing agents?
Yes.
Would fluoride ions, listen to me very carefully, would fluoride ions make good oxidizing agents?
No.
Horrible. Why?
They don't want to go more.
Okay. Because if fluoride ions, if you answered yes, if fluoride ions try to act as oxidizing agents, what are they going to do? They're going to gain more electrons. So the fluoride ion would take in another electron and become F2 minus. In your esteemed chemistry careers, have you ever seen F2 minus? Doesn't exist. Why?
Because it has like a there shell.
Yeah, it only needs one electron. Now we're going to have like an extra chihuahua way out there, which isn't going to be stable. So fluoride ions, okay, are not going to take in an electron and turn into F2 minus. Horrible. Not going to happen. Fluoride ions don't want to do anything. Why do they not want to do anything?
Shell is full.
Yeah, they're the most stable form. Now, what about fluorine gas? Would fluorine gas, listen to me very carefully, would fluorine gas make a good oxidizing agent or a reducing agent? Oxidizing agent. Fluorine gas is a tremendous oxidizing agent. Why?
So once you gain electrons.
Because it wants to take electrons and turn it into fluoride ion. Would potassium ions be a good oxidizing agent?
No.
Horrible. Why?
They don't want to get electrons.
So they do not want to go in this direction. Okay? They do not want to go in this direction. They're like, no. Okay? Because if it takes an electron and it turns into elemental potassium, and let's say, for example, that happens in water, if it does happen to take in an electron and you make an atom of pure potassium, and you're in water, what's the only thing it's going to do? Explode and go back to being a potassium ion. Okay, it's like, screw that. No. So here's what you have to understand. You have to understand what's the most stable form of these elements. Are they most stable as ions? Or are they most stable as the elemental form of this? Okay, that's the fundamental crux of this. Look at the big three elements we use in jewelry: gold, silver, copper. Why do we use those three in jewelry?
Because they want to be in they want to like not be ions.
Yeah, they want to be in the stable form. If gold readily turned into an ion, it's like, oh, here's a gold ring, dear. It's forever. First time you wash your hands, whatever the gold ring, I don't know, it dissolved. That sucked. Okay? Someone gives you a sodium necklace for your birthday. Okay? Why do you not want to wear a sodium necklace? Huh?
Because it would explode when you get
What's a nickel?
Oh. The thing you wear.
Oh,
It explodes when you jump in the pool.
what he said.
Or if you sweat?
Yeah.
That too, yeah.
Yeah.
Like a shot copper.
Yeah, kind of. Yeah. Okay.
It starts to
Not good. Okay. Now, so the best oxidizing agents would be on the top left side of this chart. Okay? Where would the best reducing agents be?
Bottom right.
Bottom right. Why?
Because it's the opposite.
Because the bottom right, you have elemental sodium, you have elemental potassium. Those are your best reducing agents because they want to get oxidized and go back in that opposite direction. So those are your extremes. Okay? Those are your extremes. Now, here's typically how questions play out relating to this. So let me give you this question. Speaking of silver, let's say I gave you this question. Are hydronium ions capable of oxidizing Ag? Now, I put the into Ag+, but a lot of times on questions, this isn't necessarily given, okay? But I would have said, okay, hey, it's going to turn into Ag+. So here's how this would physically play out. Bless you. What would happen is that you would have a solution of like hydrofluoric acid, you'd have some acidified solution. you'd have hydronium ions, right? And you would drop into this thing a chunk of silver. Is the reaction going to take place? No. Olivia?
No.
Why?
Because I don't know. I feel like it went
Just
away.
You talk about jewelry. Yeah. The jewelry thing. Richard, no, Michael, let someone get this one.
I got the sequel.
Oh, no, I'm not gonna let him let you off the hook on this one.
You are, you're not.
I'm not.
Oh, gosh, dang it. I don't even know what I'm looking at right now. Okay.
Where's the best policy?
I don't know. It would make it negative? Like the E number? I don't know.
How would it make it negative?
I have no idea.
I like how you have help from your comrades.
Jeopardy phone friend.
Phone a friend.
I don't even know what they're telling me right now. That's how confused I am.
Okay, look at it this way. Silver would have to turn into Ag plus, right? So if you look on your chart, which direction is silver written on here? It's written as Ag plus an electron turning into Ag, right? That's how it's written. And going that way, that has a positive value of 0.80, right? Okay? Go with that. So if this happened, the silver would turn into Ag plus. It would lose an electron. It would get oxidized. This would get reversed, right? What would be the sign of your E naught value? The negative value. Now, look at your hydrogen. Your hydrogen, which is defined as a relative value 0, so that one, here's what would happen. If this reaction took place, this is physically what you would see taking place. You would see bubbles of hydrogen gas forming, and you would see the silver dissolve. Okay, that's what you would see happening. If that took place, what would be the sign of your E naught value? Negative. Because you'd have negative 0.8 plus 0, which would get you a negative 0.8 non-spontaneous reaction. Again, this is why you use silver in jewelry. Okay? Does pure water have some hydronium ions in it? Yes. What's the concentration of hydronium ions in pure water? 1.0 times 10 to the negative 7th?
Oh, yeah.
Yep.
Yeah.
I said same with the OH. I said that.
Yeah, same.
Same as the OH. So even in pure water, you have some hydronium ions. So if silver was oxidized, you take a bath, you get water on your silver jewelry, what would happen? It would dissolve. If this happened. Okay. Now, what if I ask you this? Is H plus capable of oxidizing magnesium? Ooh. That's an ion. Yes. Absolutely. Why?
Overall, it's a negative EV.
It's like 2 point. Oh, it's 2.21 positive as E naught, so you do good.
So perhaps if I take a small piece of magnesium and perhaps I drop that into a solution with hydrochloric acid.
Oh, it got everywhere. No.
So we do this. Answer, is it capable of it?
Yeah.
There you go. You're generating hydrogen gas. Hold on. Stop that. I can do it.